our design, we chose a scissor lift, which allows us to fit within the box while still being able to lift above the wall. We use a gear rack to drive the pegs together and lift the bucket.
In addition, if the scissor lift does not work during the competition, our drivetrain allows us to go up both slopes of the ramp, so that way we have a backup plan.
Our scissor lift is driven by a laser-cut Delrin gear rack. It is connected at the top by aluminum rods, which are spring-loaded, and the back of each side is tap drilled, while the front has free-running nylon bushings.
The front panel is connected to a servo motor with string, which allows us to pull it up to get the bolts off of the wall, and then it is also spring-loaded with a torsion spring in order to have its resting position to be open.
For our drivetrain, we powered the back two wheels using two screwdriver motors. These motors were connected to the front two wheels via two timing belts. In using timing belts, we were able to reduce the amount of torque needed.
The first big change was using a movable front panel in order to minimize the friction of the balls against the wall. The next big change was using a single-piece gear rack that we laser cut out of Delrin. Finally, we changed our scissor lift driving mechanism from 2 to 1 motors so that the scissor lift could be lifted in unison. Over the course of the semester, we learned the importance of using calculations such as those for moment and torque to ensure that our design of the scissor lift was actually feasible.
We also learned the importance of supporting our shafts on both sides to minimize beam bending and also ensure that our gears mesh well.